Hi everybody, welcome to another video in Calculus 2. We go to a new chapter, power series. Compared to previous chapter, this series now we have a variable x in it along with the index k. So here we have k is the index. With the power series that we study, we have an x in it as well. So when we talk about power series, it is the power of x in the series. And because the index go from 0 to infinity or 1 to infinity, doesn't matter. But those only take whole numbers as a value. Right, we could have x to the k, or we have the power of x minus a to the k. In this case, a is a constant. And this a is called the center of the power series. So we either have power of x or x minus a. By the way, if we just have x, this is like x minus 0 to the k power. So this is center at 0. C sub k is also a constant called coefficient of the power series. Yeah, so yeah, a is a center of series. I already have that. Right, so now, so what do we need a power series? So remember one of the problem that we did earlier, and there's some certain integral that we cannot integrate. For example, if we have this, then we cannot integrate. Usually, if we cannot find the exact solution, we find the approximation. Like most of the time, we do that. So the point here is we use the power series to approximate the function. And we did this in Calculus 1, like the equation of a tangent line or linear approximation. So for example, we have a curve. To estimate a curve, we can use a line tangent to a point. So the approximation will be very good if the point is close to the point of tangency. If the point is around this point, it will be good. If the point way out here, the function and the approximation will be way off. So the closer it is to the point, the better. So we have a curve and we'll try to approximate that. This is one way to do it. Now if we want to be a little more accurate, instead of using the line to approximate a curve, we use the second degree polynomial or a parabola to approximate it. So this curve is getting closer and closer to the actual curve. And of course we can get to higher and higher degree polynomial to estimate. But first, let's look at some basic one. We use the linear approximation. By the way, this is in Cal 1 already. So derive the first degree polynomial of the linear function. So the one here corresponding to the first degree polynomial that approximate the function. So that's the subscript 1. And so we'll have the values of the function, and we have the slope, which is the derivative at the point. So we will try to find the equation of the tangent line, pretty much. So we have the values of the linear function is the same as the function, and the derivative will be the same as that. So we know the values of the function and we know the slope. Right. So how do we come up with the equation? The line, the equation of tangent line b sub 1 p1x. Right. So what we do with, we will start with this derivative. With this. And instead of writing a, we're going to use x. And the derivative is equal to derivative of the function and that derivative is that. Now, but furthermore, it's going to be equal to a constant. Yeah. So because this is a straight line, so derivative is a constant. And that constant is equal to f of a. So instead of equal to f of x, this equal to f prime of a. Because the linear function derivative is constant. Like mx plus b, derivative is the constant m. So we start with that. Now, if we have the derivative, to get back to the function, we will integrate that. This is the constant. Integral of constant is that constant times x plus c. So we have this. Originally we have derivative equal to constant, integrate, and we have this. Now we have the initial condition at x equal to a, the values of the function at a equal to f of a. So we substitute a in here. And we have P1 of a, which is f of a equal to f prime of a, and x equal to a and c. From here we can say that c is equal to f of a minus f prime of a times a. C equal to f of a minus f prime of a times a. Then we substitute this. Into this c. So we have P1x equal to that. Derivative x plus f of a minus f prime of a times a. Then both of these have derivative. Factor it out. We have f prime of a x minus a plus f of a. Or we can write as f of a plus derivative x minus a. Right. So that is the equation of the tangent line, or we can also call the linear approximation. So we can use this to estimate the values of the function using the tangent line. Right. Next we'll do the same thing, but this time we use quadratic approximation, meaning we use a parabola to estimate this. Right. Try to write smaller because we might not have a lot of space here. Right. So for the second derivative, we have second derivative is given, first derivative is given, and the values of the function is given. So in the linear approximation, we have the values and derivative same as the function. For quadratic function has three coefficients, right? So we're going to need three things: the function, derivative, and second derivative of the quadratic So what we're trying to find is the equation of this one, the quadratic approximation. So the quadratic approximation and the actual function, we have three things in common. The function first and second derivative that are the same, 1, 2, and 3. Right. Now, similar to what we did on the previous example, what we do is we start with the second derivative, integrate, and just solve for like the initial value problem, very standard initial value problem. So this time we start with now for the quadratic, this is the second degree, so we're going to have p sub 2. So at p sub 2 of x equal to, given is going to be the derivative. Now, if we want to undo the derivative, we do the antiderivative or the integral. So p2 of x equal to integral is of the constant that is the constant times x plus c. Now this way we start with the second derivative, sorry. And when we undo it, we have get back to first derivative. Sorry, that should be the case. Second derivative, integral, give us back to first derivative, and integral again will give us back to a function. Right, but first we have to solve for this c. To solve for this c, we have this initial condition. At x equal to a, the first derivative is given. So put a in here, we have p2 prime of a, which is f prime of a, equal to second derivative x is at c, at a, sorry. C. Now we solve for c, move this to the other side. C equal to first derivative minus second derivative times a times a. And I substitute this back into c. So I will have second derivative times x I'm going to write this one first though. There are two terms, so I'm going to minus first. And then f prime of a. I'm going to write like that instead. So when it's like this, we can factor out the second derivative. So we'll have second derivative. Sorry, not second derivative. The derivative equal to second derivative of the function. Factor that out. X minus 8 plus the derivative. Right, so that is the derivative. Now to undo the derivative, get back to the function. So this is what we have. Now undo it integrate one more time. P2 of x equal to integral right, and we integrate that. Integrate this, we have the second derivative. Integral of x minus a is x minus 8 square over 2. And derivative, that is a constant actually. So we multiply x and then just plus c. Now we're going to use this initial condition at x equal to a. P2 of a is f of a. So put f of a in here. Second derivative, a. Here we have a into x, a minus a. And the first derivative at 8 plus c. Now this a minus a go to 0. So pretty much the c is equal to that. I'm going to write this negative f prime of a times a. Move that to the other side, then plus f of a. And finally, if you substitute this into this c, we have the equation P2 of x equal to, I've run out of space, so I will just write this f second derivative at a, here, x minus a square over 2. And now we skip a step and we have derivative x minus a and then plus c. Later on there will be just a formula for this, and so we don't have to derive this every single time. But that's what we have. So this is the linear, not c, sorry, plus f of a. So this is the equation of tangent line. Adding a term to it, the equation of the quadratic that estimate the function. So quadratic approximation is given by this. Right. So let's just look at the example and see how good this approximation is. Right. Find the linear approximation near x equal to 1 for the function f of x equal to ln of x. If f of x equal to ln of x, then derivative is equal to 1 over x, or x to negative 1. So the linear equation, the first order approximation, I'm just going to write it out. So we did this earlier, and this is what we have. So P1 equal to the values of the function at a plus derivative at a and then x minus a. So in this example, a is 1. So we have P1 of x equal the function at 1 plus derivative at 1 and then x minus 1. Right, so simple enough, right? So f of 1, the function is ln of x. ln of 1 is 0. And f prime of 1, the function is 1 over x. 1 over 1 is 1. So we have 0 and this 1. So this is just x minus 1. Let's see how that works. So we have the equation ln of x, that the function, and the equation the tangent line x minus 1. Right. So let me zoom in. Right. So that is that. Now estimate the values of the curve. We can use the line, but have to be close to x equal to 1. So closer to x equal to 1, the approximation is good. If it's further away from it, it's not a good approximation. Right? But it's a tangent at 1. Right? So that is the linear function. Now, if we want to use the quadratic approximation, the x equal to 1 quadratic approximation is given by this. Right. Actually, I'm going to write this in the increasing order of derivative. So p2 of x equal f of a plus derivative at a plus second derivative at a over 2 x minus a squared. So we have a quadratic. Right. And in this case, once again, we have a equal to 1. So we're going to say p2 of x equal to the values of the function at 1, derivative at 1, second derivative at 1 over 2 x minus a squared. A is 1. Right. So we have the values of function equal to 1, derivative equal to 1, second derivative of this negative x to negative 2, or bring it down negative 1 over x squared. So second derivative at 1 is negative 1 over 1 squared. So negative 1. So this is negative 1/2. So we have f of 1, which is 0. Derivative is 1. And this is negative 1 over 2, negative 1/2. So when we substitute everything in, we have x minus 1 minus 1/2 x minus 1 squared. Right. So let's graph that and see what happened. X minus 1 So I have ln of x, and then we have the approximation. it helps if I type that correctly. X minus 1, sorry. Never mind. Right, so that's the function. Now to see the approximation will be very close to it. Now to see the parabola approximation is a lot better than the line. So when you get close to the point, the quadratic function get close to the curve. So this is a good approximation. Right, so that's the idea. Right, and of course, if we want to, we can use not only the function first and second derivative, we can use third derivative and so on. So that idea of what we did in general, we have a Taylor polynomial. So when we have the n order polynomial, meaning that we know the n derivative along with the function, give us the n order polynomial, and we will denote that by piece of n, and have the values, the slope, second derivative up to that. So we have the values of function, derivative, second derivative, and then so on all the way to the n order derivative. In that case, you recognize that we see this before, right? So linear function, quadratic linear approximation, quadratic approximation. We just keep going. So the general formula is we're going to have the n order derivative divided by the n factorial and to the n power. So those all of that to the n. So we can write like this: the power n order Taylor polynomial will be given in this form. The coefficient is given n derivative. Oh, sorry, this should be k. K derivative over k factorial evaluate a, and then x minus a to the k, the same thing. Right. Usually we do this. We will do that in the table, so it's easy to organize things. Right. Now let's look at the first example. Now find the Taylor polynomial of order n 0, 1, 2, 3. Actually, we're just going to do 3, and then we just chop it up whenever we want to. For cosine of x, center x equal to 0, use the polynomial to estimate cosine of 0.1 and absolute error f of x equal to p of n plus x. Just do it for 3. We don't need to do that for every one of them. Okay. Now, so k will be equal to 0, 1, 2, 3. So we start with that. Now this one we have f the k here in the parentheses, meaning we will take derivative. We start with cosine of x. Derivative of cosine of x is negative sine x. Derivative of negative sine x is negative cosine of x. And derivative of negative cosine x is sine x. Simple enough, right? Function first, second, third derivative corresponding to the index. Next, evaluate that at a. In this case, since center at 0, so a is equal to 0. So we're going to put 0 in all of this. So we have cosine of 0 equal to 1. Negative sine of 0 is 0. Negative cosine of 0 is 1. Negative. And sine of 0 is 0. Simple enough, right? All derivatives put in the values. Next, we're going to take whatever we have here, divide by the k factorial. So we have 1 over 0 factorial. By the way, if we want to do the factorial, 0 factorial by definition is equal to 1. Or if we want to 0 hit math, go to the probability tab, option number 4, This one. So 1 over 1 is 1. Next, 0 over 1 factorial. 1 factorial is 1. Now we have negative 1 over 2 factorial. 2 factorial is 2 times 1, which is 2. And 3 factorial. 3 factorial is 6. Doesn't matter though. 0 divided by 6 is 0. So that's what we have. That is what we have. So if we want to write a piece of 3 Taylor polynomial of order 3 is going to be equal to 1. This is only the coefficient though. In here we still will have the coefficient. Those are C of k. But then we still have to have the power part of it. So this is x minus 0. Here for k equal to 0, so power will be the same. Next, we have 0. That's the coefficient times x minus 0 to the first. The next coefficient is negative 1/2. For k equal to 2, so x minus 0 to 2. The next coefficient is 0. We should have x minus 0 cubed. And this can go on forever. But this is simple enough. We just have this is just x. Sorry. This is just 1. Because anything raised to 0 powers. Unless of course at 0, then it's still. But anyway, just x to 0 powers 1. That one gone. Minus 1/2 x minus 0 square, or just have 1 minus 1/2 x square. Right. By the way, if we want P2, that is P2. If we want P1, that is P1. Right? So those will give us the coefficient. And we just have the power corresponding to 0, 1, 2, and 3. X minus the center raised to that power 0, 1, 2, and 3. Right. So will be that. Right. And we're going to use this to approximate cosine of 0.1. So we have 1 minus 1/2 of x, which is 0.1 square. So we will say cosine of 0.1 approximately equal to, we're going to use this 1/2 0.1 square, and we have 0.995. Right. So in this chapter, this skill is very important. If one thing that you need to remember from this chapter as long as possible, it will be this: how do we construct a Taylor series using something, a table like this. So we do a lot of example. Right, so that is the approximation. The actual values is that in radian? Yes. Cosine of 0.1 is 0.9950042. This is the exact values. Of course not exact, just keep going. And we use a calculator. And then the absolute error, we just subtract the two. So 0995 minus that. So we just take this number, just take the bigger one, subtract the smaller one. Right, so we have that. So this is extremely accurate. Yes. Let's look at the graph and see what happens. We have cosine of x and 1 minus 0.5 x squared. So that is cosine. And then we have the parabola will be extremely close to it. And when we have 0.1 here, the point you see extremely close to the actual curve from the parabola. So that's why this is a very good approximation. Right, so get used to doing the table like this. Once again, we're going to list all the k index. 0, 1, 2, 3, and 4. And then we will write out the function and check the derivative successively. Sine of 2x. Derivative of this is going to be 2 cosine of 2x. Keep taking derivative of this. It is going to be so this is the function. This is the first derivative. Let's just denote here function derivative, second derivative, and third derivative. Right, so function derivative, and then just keep taking derivative. It's going to be 2 derivative of cosine. This is negative 2 sine of 2x. So give us negative 4 sine of 2x. And derivative of this is negative 4 sine of 2x is 2 cosine 2x. So negative 8 cosine 2x. And do that one more time. We have negative 8, negative 2 sine 2x. So that gives us 16 sine of 2x. So what we have is function first, second, third, and fourth derivative. Now, evaluate this at pi over 4. That is the center. So just evaluate at pi over 4. Right. Sine of 2 times pi over 4. So sine of pi over 2 is 1. Next we have 2 cosine of 2 times pi over 2. Pi over 4, sorry. So that gives us 2 cosine pi over 2, cosine pi over 2 is 0. So this is equal to 0. Next we have negative 4 cosine, sorry, negative 2 sine of 2 times pi over 4. So negative 4 sine of pi over 2. Sine pi over 2 is 1. So this is negative 4. 1, 0, negative 4. And then we have negative 8 cosine 2 times pi over 4. And cosine pi over 2 once again is 0. and then 16 sine of 2 times pi over 4, 16 sine pi over 2. So kind of small, but it's not that bad. Just the kind of routine type. Sine pi over 2 is 1, so we have 16. So the coefficient is 1, 0, negative 4, 0, and 16. We're going to divide by the factorial. 1 divided by 0 factorial, which is 1. 0 divided by 1 factorial, still 0. Negative 4 divided by 2 factorial. 2 factorial is 2. So I have negative 2. 0 divided by 3 factorial, doesn't matter, still 0. 16 divided by 4 factorial. So the order of derivative will be the same as the factorial. 16, 4 factorial is 4 times 3 times 2 times 1, which is 24. 16 over 24 is 2/3. So the coefficient is 1, 0, negative 2, 0, and 2/3. The center is pi over 4. So this is the 4th degree polynomial. So we're going to write P4 of x, the 4th degree. Now, first coefficient is 1. And we will have x minus the center to the 0 power, because that's where k equal to 0. Next, coefficient is 0, corresponding to k equal to 1, which is x minus pi over 4 to the first. And then the next coefficient is minus 2. We have x minus pi over 4 over 2. Next coefficient is 0, corresponding to k equal to 3. So x minus the center cube. And next we have 2/3. X minus the center to the 4th. So we will have anything raised to 0 powers. Anything to raise to 0 power is 1. So we're going to have 1. And that's 0, minus 2. X minus pi over 4 square, and plus 2/3 x minus pi over 4 to the 4th. Right, so that is the 4th degree polynomial. Right, we can even graph it and we see how good it is, the approximation is. One minus 2 x minus pi over 4 square plus 2/3 I don't have to do this every time, but just want you to see what it look like. So we have sine of 2x, look like that. Now pi over 4, I guess is around here. Yes. Pi over 4. So you see, what is pi over 4? pi is 3.14 and divide by 4, so it's around here. So the approximation will be very good. You see almost that part around that point, the curve and the polynomial, the sign of 2x and the polynomial almost identical for a big chunk of the function. So the approximation for that part will be very good, right? So around pi over 4, so be around here. So those part of the sine of 2x and the 4th degree polynomial almost identical. So that's a very good approximation. Again, the index function and then take derivative, evaluate at the point, and then divide by factorial. And then finally, we just have that with the power of x minus the center to the corresponding k power. That gives us the Taylor polynomial. Like I said, very important. So this chapter, you need to know how to do that. Right. Now this is less significant remainder in Taylor polynomial. So how good is our approximation? What is the worst case scenario for our approximation? So we define the remainder is equal to the actual values minus the approximation, the function approximation. And the Taylor theorem says that. So this is the error. Or could be, if we take the absolute values, that will be the absolute error. Let f have continuous or all of derivative. So we have defined, now we just move f of x, we move that to the other side, or we just have the same thing as the remainder as before. And we said for all x in the interval, the remainder is equal to this. So what is C here? C is a point between x and a. So the difference between the actual function and the approximation is different by this much, where there will be a point C somewhere in between x and a. Right. Now we also have this term, the worst case scenarios. The worst case scenarios, the absolute error or the absolute values of the remainder different between the actual values and the approximation is no more than this. So where m is this, m such that c is between a and x inclusively. So m is the maximum values of f of x, maximum values of the function from a to x. Right. So m max values of the n plus first derivative from a to x, or from x to a if x is less than a. Right, so how does that work? Right, we'll go back to that, but first let's look at one more example. Now we will calculate this in a minute. Right, first estimate the approximation of that using Taylor polynomial of degree n equal to 4. So we will go from 0, 1, 2, 3, and 4. Now this time I choose something e to the x because the function is e to the x, all the derivative is all from e to the x. Then we evaluate at center at 0, meaning a equal to 0. So we'll put 0 in here. E to 0 power is 1. So all of them e to the x at 0. So all of them equal to 1. And next we will just divide by the k factorial. 1 divided by 0 factorial 1 divided by 1 factorial. 1 divided by 2 factorial, 1/2. 1 over 3 factorial, 1/6. 1 over 4 factorial, 1 over 24. So those are the coefficients put in the Taylor polynomial of order 4. Right, first the coefficient 1 corresponding when k equal to 0. So we have x minus the center at 0 to the 0 power. And next coefficient is also 1, x minus 0 to the first. Then 1/2 x minus 0 square, 1/6 x minus 0 cubed, 1 over 24 x minus 0 fourth. Of course 0 is the center, so we have x minus the center raised to the k power. So those are the coefficients, and those are the polynomial. Right, x subtract 0, so we just have x, the first one to the 0 power. So this is just 0, so 1, and then this is x, 1/2 x squared, 1/6 x cubed, 1 over 24 x to the 4th. Right, so that is the 4th degree polynomial, and I'm just curious to see how that looks compared to the actual function. The function is e to the x. One plus x plus 1/2 x squared plus 1 over 6. You don't need to do that for the actual problem. Just see that it looks nice and all. X to the 4th. Right, e to the x, and then we have the 4th degree polynomial. Right, so once again, exponential function, and then we have the 4th degree polynomial. You see, almost identical to it. The center at 0, so when it goes to close to 0, the approximation is very good. Right, now we will evaluate the values. We want to find EF to the 0.45. So on the calculator we can do that easily. Calculator e to the 0.45. We have that much. Now, if we want to evaluate this at the same values, now the good thing is I already entered that into y2, right? So there's a couple of ways to get to y2. Either we hit variable, y variable function, that's y2, or if your calculator allow, we hit alpha trace y2 at 0.45. $1.568 146. That's good enough. Now the error. This is the actual values. Subtract the approximation. We have that. So absolute error. The actual values minus approximation. As you see, we only have 4 terms and the approximation is very good already. Now after this section, then you get the idea of how the calculator can evaluate sine, cosine. Of course, they cannot just memorize all the values. What the calculator does is they store a function, and that's pretty much just a Taylor polynomial. And let's ask what is cosine of 0.1. They will just put 0.1 in the corresponding polynomial that the calculator store the values. So that in that case, the calculator can evaluate the sine, cosine on the trig function or any other function. So they represent that trig function by one polynomial, and then whatever the values we put in, they just put in the polynomial, and that's what the calculator calculate, and that the calculator calculate. It could get extremely as accurate as we want to if we just have more terms in the polynomial. Yeah, but this is relatively good approximation, right? So it's just like that. However, I just want to do one more thing. What is the worst case scenarios for the error, right? So this is the actual error. We use the calculator. Let's say if we don't want to do any of this, we say what is the worst case scenarios. If we go up to 4 terms, what is the worst case scenario? So in that case, first of all, we have to find m though. Right, first we have m is going to be bigger or equal to, it's going to be n plus 1, so it's going to be n is 4, so it will be 4 plus 1 derivative at the point C. So what's that? Right, for derivative, so the fifth derivative luckily is still e to the x. Now, and c is between 0 and 0.45. So for x between 0.45 and 0, you say what? You get the idea 0.45, right? Because the actual what we need to evaluate, what is the 0 is the center. So from 0 to 45, we're going to pick the biggest number to make ever the fifth derivative to be the biggest, right? So from 0 to 0.45. Now the exponential function going like that. So the biggest one is at 0.45. So m we can set to be the maximum of on the fifth derivative, and the fifth derivative is maximum at this values. So m is equal to e to 0.45. Right? Exponential function, the maximum will be at the end point. So m is equal to that. And finally, we just take m times x minus 8. So the error, I apologize that we run out of space here, but the error, the remainder, will be no more than m times x minus a to the n plus 1 over n plus 1 factorial. So we have m is e to the 0.45 I don't know why I put a decimal there. X minus a, x is 0.45 and a is 0 to the 5th power over 5 factorial. So this is the worst case scenario. The error will be this big, e times 0.45 45 times that just times that just 0.45 to the 5th power divided by the 5 factorial, which is 120. Right, so m worst case scenario, the maximum of all derivative is that, and we have just put everything in here. So the worst case scenario is will be no more than this. The actual calculation we have the error is this much, but we know before we do any calculation we know that the maximum error, if we go up to 4 terms, and not 4 terms, if we go up to the 4th degree, the worst case scenario for the error is this much. When we calculate the actual error is even, of course, should be less than this. Right, so that's what this formula is about. So we find m, which is the biggest values of all of the n plus first derivative on the interval. Because e to the x is increasing, the end point will give us the maximum, and we just put in the formula. That's what we have. So this this calculation will tell us what is the worst case scenarios for the error. What is the remainders less than or equal to? This is the worst case scenario for the error. The actual error should be less than that. So that's what we have. Right. So we will do a few more examples using the table like this. So this is very fundamental. We use this table to find the Taylor series, or just in this case, just Taylor polynomial. Because we can do this indefinitely, but the basic will be this. Anyway, I stop section 11.1 here. See you in another video in Calculus 2. Thank you for watching.